Hello everyone. In this session, we are going to discuss vector calculus. By vector calculus, we understand that the calculus that deals with the differentiation and integration of vectors. That is called the vector calculus. So, the applications of vector calculus can be seen in many fields like electricity, magnetism, fluid flow, gravity. So besides all of this, there have many applications of vector calculus. So in this session, we are going to talk about particularly on gradient, divergence, and curl. So besides gradient, we have to know what is directional derivatives. So gradient is denoted by grad f. Divergence is denoted by div. Curl is denoted by curl f. So besides this notation, we can see there is another notation for these three quantities. We can see that an special symbol which is known as del. It is also known as inverted delta, or it is also called nabla. But here we will pronounce this one as del. So del is a vector differential operator. That means del is a vector which is equal to ddx in x direction plus ddy in y direction. So this is the two-dimensional form of del. If we want to know the three-dimensional form of del, then this is denoted by this way: ddx in x direction plus ddy in y direction plus ddz in z direction. Here I, j, and k are the standard basis vectors in x direction, y direction, and z direction respectively. So with this del symbol, we can represent gradient divergence curl. That is, gradient equals grad f, that is del f, where f is just a function of two variables or three variables. That means function of several variables. Divergence can be denoted by del dot f, that is divergence of f. Curl is denoted by del cross f. So it is also known as curl f. Besides gradient, we have to know another term, that is directional derivatives. So directional derivative is denoted by this form. So vector calculus can be used to describe real life phenomena like this. Let's say we want to know the temperature from the northern part of our country to the southern part. So the temperature is changing with respect to distance. So if we need to find the rate of change of temperature in this direction, then we have to apply the concept of vector calculus. We can see here in this figure and this figure denote the rotations of a tornado. So we can see that around this point there is a rotation. Around this point we have the rotation. So if we have to measure the rotation, then we need to apply the concept of vector calculus. Specifically, we need to apply the concept of curl. In this figure, we can see the air particles are moving around. So the flow of the air particles are denoted by these arrows. So from this figure, we can easily understand the flow of the air particle over a region. So this is an example of vector calculus. In this figure, we can understand that the air particles or fluid particles are diverging from this point. So this is one example of divergence. So by divergence, we can understand the tendency to diverge from a point. So by divergence, we can also understand whether a fluid is compressible or incompressible. In this figure, we can understand that the temperature from this point to this point is changing. So if we need to have the rate of change of temperature along this direction, then we have to apply the concept of gradient, specifically directional derivatives. So these are the real life examples of vector calculus. So that means we are dealing with vectors every time. We know that velocity and acceleration are the examples of vectors. Vectors are the quantities that have both magnitude and direction. We can see that the direction can be visible. So, in a word, we can say that vector calculus is very important to model the real life phenomena. So, before starting vector calculus, we have to know what is vector. Vectors can be two-dimensional or three-dimensional. So, vectors are the quantities that have both magnitude and direction. So, a vector can be written with a letter. It may be a small letter or capital letter. But whenever we denote a vector, we use either bold form, that is the bold face, or we put an arrow sign above that letter. So this is how vectors can be denoted. So any vector can be represented by, let's say, a1 I plus a2 j plus a3 k. So here I have denoted I with hat symbol. So these are denoting the unit vectors, which are also known as standard basis vectors. So I is in the direction of x-axis, vector j is in the direction of y-axis, and vector k is in the direction of z-axis. So this is the example of three-dimensional vector. An example of two-dimensional vector will be a1I plus a2j. So this is x-axis and this is y-axis. So I is in this direction and j is in this direction. So vectors can be thought to be a point. This is the three-dimensional vector and this is the example of two-dimensional vector. So vectors are thought to be a point. Here a equals a1I plus a2j. That means we can represent in another form. We can represent a1I plus a2j as a point a1 comma a2, or we can also denote by this way, a1, comma a2. The three-dimensional vector a1i plus a2j plus a3k can be denoted by a point a1, a2, a3, or we can denote by this way, a1, comma a2, comma a3. So vectors can be represented by this way or this way. We can also represent a vector by this way, a1, a2. This is the representation in row wise, and this is the representation in column wise. Similarly, the three-dimensional vector can be represented in column. So a1, a2, a3. So before starting vector calculus, we need to have a strong knowledge on vectors. So we have to know what is the meaning of position vector, how we can measure the length of a vector, what is unit vector, how can we find the unit vector of any vector, what is dot product, and what is cross product. So we have to know all these concepts first, then we can move to the vector calculus. So first we are going to discuss about vectors. So a vector in two dimension can be a equals 2i plus 3j. So we know that any vector can be represented by a point. So we can also think about 2 comma 3 or 2 comma 3, or we can represent this same vector as column wise. So this two-dimensional vector can be plotted in this Cartesian plane. So we have x-axis and y-axis. So any vector is a point. So we have 2 comma 3 point. We know how to locate a point in Cartesian plane. So 2 comma 3, that means 1 2 1 2 3. So we can locate this vector. So the point is 2 comma 3, 1 2 1 2 3. So this is the point, which is 2 comma 3. So up to now we have just located the point, but since it is a vector, so always it will be directed from the origin O. We know that the coordinate of the origin is 0 comma 0. So always any vector is directed from origin to the point. So this is our vector, which is known as A equals 2i plus 3j. So this is called position vector. That means we have understood the position of this vector. We have to go two distance in x direction, and in y direction we have to go three distance. Then only we can locate this point. So that means the position of this point is now known to us. So the vector that is from origin to this point, let's say this is the point P. So the vector A is called the position vector, or we can say A equals OP. That means it is directed from O to P. So any vector is written as boldface or letter with an arrow sign. So an arrow has an initial point and a terminal point. Here, this arrow has an initial point and a terminal point. The initial point is called the tail, and the terminal point is called the tip. So we can understand that any vector is starting from here and ending at this part. So this is how we can locate the position of any vector. So this is the representation in 2 dimension, since this is a 2-dimensional vector. So similarly, we can think about a vector in 3 dimension. Let's say we have 2i plus 3j plus 4k. So this is a vector in 3 dimension. So in 3 dimension, we have x-axis, y-axis, and z-axis. In previous example, we have only x-axis and y-axis. So since we have two axes, we can call this one as R2. That means we have a real axis, we have another real axis. So that's why it is called R2. Or we can say this is the 2-dimensional surface. Similarly, if we have x-axis, y-axis, and z-axis, so this is denoting R3. That means we have 3 dimension. This is a real axis, this is another real axis, this is another real axis. So we can understand this one by an example. Let's say we have a room where this is the floor, this one is the right wall, and this one is the left wall. So this is x-axis, this is y-axis, and this is z-axis. This is the corner of a room. So we can say that the floor is the xy plane. The right wall consists of y-axis and z-axis. That's why it is called yz plane. And the left wall is called the xz plane. So this is what we know as R3. So this vector can be a point, that is 2, 3, 4, or 2, 3, 4. We can represent the vector in any of the form. So now we need to know the position of this vector. So we can understand that in x direction we have to go 2 distance, so 1, 2. In y direction we have to go 3 distance, 1, 2, 3. In z direction we have to go 4 distance, 1, 2, 3, 4. So now we can easily locate the position of this vector. So 2, 1, 2, then 3, 1, 2, 3. That is the parallel line of y-axis. Now we are here. So we need to go 4 distance vertically. So let's say 1, 2, 3, 4, which is the parallel to z-axis. So now we have reached to a point that is 2 comma 3 comma 4, that is 1 2 1 2 3 1 2 3 4. So this is the location of the vector. So we can represent the vector from origin. So from origin to this point, this is the direction that we have. So this OP or this A is called the position vector. That means any vector can be directed from origin always, no matter whether we have R3 or R2. So this is how we can describe position vector. Now we need to know what is the component of a vector. So let's say we have a two-dimensional vector a1i plus a2j. Similarly, we may have a three-dimensional vector a1i plus a2j plus a3k. So we can write in alternate form a1 comma a2. For this one, we can write a1, a2, a3. So these are separately called components. Similarly, here a1, a2, and a3 are separately called the components of the vector A. So a1 and a2 are the components of this two-dimensional vector. For this example, a1, a2, and a3 are the components of a three-dimensional vector. So that means if we have a vector, let's say a equals 2i plus 3j, that means this 2 and 3 are the components of this vector. Let's say we have a three-dimensional vector b. We can use any letter to denote a vector. So b with an arrow sign, this is a vector. So b equals, let's say we have 2i plus 3j negative k. So that means we have the point 2 comma 3 comma minus 1. So separately, all these parts are called the components of this vector b. That means 2, 3, and minus 1 are the components. We can compare with a point x comma y. So that means a1 is the component in x direction, a2 is the component in y direction. For three-dimensional part, we can think about x comma y comma z. So a1 is the component in x direction, a2 is the component in y direction, a3 is the component in z direction. And we have learned that in x direction, we use I hat. In y direction, we use j hat. And in z direction, we use k hat. So that means this is the component in x direction, this is a component in y direction, and this is the component in z direction for this vector. So now let's talk about how to find length of a vector. So let's say we have a vector a equals 2i plus 3j. So this vector can be thought to be a point 2 comma 3, that is in x direction 1 2, in y direction 1 2 3. So that means 1 2 1 2 3. So this is the position of this vector A. So any vector is directed from origin to that point and always directed by an arrow. So here the vector is this one. So if we want to find the length of this vector, we want to know the distance from O to this point, let's say P. So the length is this one. This yellow color part is denoting the length. So this vector is in R2. That means it is a two-dimensional vector. So if we have to find the length, then length is denoted by absolute value of this vector. So we can see that there is an absolute value. So this is denoting the length. So length will be 2 squared plus 3 squared square root. This is the length of this vector. So in general, we can think like this way. If we have a vector in two dimension, let's say a1i plus a2j. So the length of that vector is the absolute value of a equals a1 squared plus a2 squared. That means this component is squared plus this component is squared square root. So this is how we can find the length of any vector in two dimension. So the result will be 4 plus 3 square root. That means we have square root of 7. So the distance from origin to P is root over 7, which is approximately 2.6458. So this is how we can find the length of any vector that is in two dimension. Similarly, we can find the length of a vector in three dimension. So let's say we have a vector in three dimension. A equals a1i plus a2j plus a3k. So the length will be square root of a1 squared plus a2 squared plus a3 squared. So suppose we have a vector a equals I minus j plus 3k. So this is the vector in three dimension R3. So this vector can be written in an alternative form. Let's say we have I plus minus 1 j plus 3k. We are following the standard form. We are writing with plus signs. So before I we have 1. So that means the point that we have for this vector is 1, negative 1, comma 3. We can locate this vector in three dimension x, y, and z. So here this is the positive x. In backward portion we will get the negative x. This is the positive y. In backward portion we have the negative y. This is the positive z. In backward portion we have the negative z. So in x we have one distance 1. In y we have negative 1. So this is the positive y-axis and this is the negative y-axis. So we have to go negative 1. and then positive 3. That means vertically upward. So let's say 1, 2, 3. So finally we reached here. This is the direction of that vector. That means the point that we have, it is here. It is 1, -1, and 3. So 1, -1, 3, 1, -1, 3. So this is how we can reach to a point in 3 dimension. So any vector will be directed from origin. So that's why we can denote from O to P. So this is the vector A. Now, if we want to find the length from O to P point, that means this yellow color part is denoting the length. So length will be absolute value of A equals A1 squared, A2 squared plus A3 squared. That means any vector has the components A1, A2, A3. For that vector, we can find the length by this way. So it will be 1 plus 1 plus 9 is square root. So finally, we are getting a square root of 11. So this is the length of this vector. So in summary, we can say that length is denoted by absolute value of that vector. If we have a vector v, then we can use absolute value to find the length of this vector. So now we have to know what is unit vector. By this term, unit, we can understand that it is denoting 1. So a vector with length 1 is called the unit vector. So definitely, if we have a vector a equals just I, b equals just j, c equals k, a equals I can be also written in another form, I plus 0j plus 0k, because we don't have any components in y direction and z direction. So that's why these are zeros. Similarly, b vector can be written in this way, 0i plus 1j plus 0k. We don't have any components in x and z direction. Similarly, the third vector can be written as 0i plus 0j plus 1k. That means we don't have any components in x and y direction. So that means this a vector can be a point 1, 0, 0. This second vector b can be 0, 1, 0. This third vector is 0, 0, 1. So this is a vector, this is b vector, and this is c vector. If we want to find the length of a, that means we know it is 1 squared plus 0 squared plus 0 squared is square root. So it will be 1. So that means we can understand that the length of a vector is 1. Similarly, the length of b vector will be square root of 0 squared plus 1 squared plus 0 squared, that is equal to 1. So the length of b vector is also 1. Similarly, the length of c vector will be 1. So that means These three vectors are unit vectors. So that's why I, j, and k, these three vectors are called the standard unit vector or standard basis vector. If we have some other vectors like v equals 2i minus j minus 2k, so we want an unit vector along the direction of this vector. Let's say the point of this vector will be 2 comma negative 1 comma negative 2. So if we try to locate this vector in R3, so it will be 1 2, then minus 1 in y direction and minus 2, so in downward z direction, so minus 1 minus 2. So that means this will be the direction of the vector. So this is O and this is P. The point is 2 minus 1 minus 2. So let's pick up this vector here. So we have the vector OP or the vector V. So the length of this vector will be square root of 2 squared plus negative 1 squared plus negative 2 squared. That means we have square root of 4 plus 1 plus 4. So that means square root of 9. So it is finally 3. So the length of this vector is 3. 1, 2, 3. So that means this is the length of this vector. 1, 2, 3. Now our target is to find an unit vector along this direction. That means there will be a vector, this one, whose length is 1 and the direction is in the same direction as V or OP. So now we need to find this unit vector. Let's say this yellow color part is of length 1. So we are denoting this one as unit vector u. So how can we find this new vector u whose length will be 1? So that can be found by this way. Unit vector u equals this vector v by the length of that vector. Unit vector is also denoted as u hat. So we can use any notation, either u hat or u with arrow. So any vector A that can be two-dimensional or three-dimensional. So for that vector, if we need to have one unit vector in the direction of this vector, then that unit vector can be defined by that vector over its magnitude or length. So this is the formula for having the unit vector. So that means we have this vector v. So if we need to have one unit vector along this direction, so unit vector can be found by vector v over its magnitude or length. So the vector is 2i minus j minus 2k over the length is 3. So the unit vector is 2 over 3 negative 1 over 3j negative 2 over 3k. So this is the unit vector along this vector. We can verify that the length of this unit vector will be 1, and this is this one, the yellow color part. So this is how we can find the unit vector. Now we have to know what is dot product. Dot product is also known as scalar product or inner product. So by scalar, we understand that it is just a number that has just a magnitude. Scalar has only magnitude, but vector has both magnitude and direction. So by dot product, we are going to have finally a scalar. So let's say we have two vectors A and B. For now, let's have a look on three-dimensional vectors. Let's say A equals A1I plus A2j plus A3k, and B equals B1I plus B2j plus B3k. So the dot product is denoted by A dot B. So the vector A is A1I plus A2j plus A3k dot B vector B1I plus B2j plus B3k. So by dot product, we will get finally a number that is the scalar. So it will be directly A1 B1 plus A2 B2 plus A3 B3. It means the multiplication of the first components plus the multiplication of the second components A2 and B2, the multiplication of the third components A3 and B3. So A1 B1 plus A2 B2 plus A3 B3. This is known as dot product of A and B. So for example, let's say we have A equals I plus 2j minus 3k, and B equals 0I plus 2j minus k. So if we need to have the dot product of these two vectors, then we can find by this way. Its component will be 1, 2, minus 3, and the component of B will be 0, 2, and minus 1. So A dot B will be the components of I and I, that is 1 times 0, plus the components of J, that is 2 times 2, plus the components of K, that is minus 3 times minus 1. So we are getting 0 plus 4 plus 3, so 7. So we can see 7 is a number, that means it is a scalar. So by dot product, we are going to have a scalar. I plus 2j minus 3k can also be written as 1, 2, comma minus 3, b is 0 comma 2 comma minus 1. That means the multiplication of the first components 1 and 0, the multiplication of the second components 2 and 2, and the multiplication of the third components minus 3 and minus 1. So this is how we can find the dot product. So this is the example of the dot product of three-dimensional vectors. Similarly, we can think about the two-dimensional vectors. Let's say we have a vector a equals 2i minus j, and b vector is I plus 3k. So if we need to have a dot b, then first let's find out the components. It is 2 comma minus 1, and the components of b will be 1 comma 3. So a1 b1 plus a2 b2. So we are getting 2 negative 3, so negative 1. This is the dot product of these two-dimensional vectors. That means if we have vector a equals a1i plus a2j, that is a1 comma a2 in two dimension, and b equals b1i plus b2j, that is b1 comma b2, then a dot b will be multiplication of a1 b1 plus a2 b2. So this is how we can find the dot product. Similarly, here we can think about a1 comma a2 comma a3, here b1 comma b2 comma b3. So a1 b1 plus a2 b2 plus a3 b3 will be the dot product of these three-dimensional vectors. And this is the formula for the dot product of two-dimensional vectors. After dot product, we have to know what is cross product. So cross product always deals with three-dimensional vectors, not two-dimensional. Three-dimensional vectors, let's say a equals a1 comma a2 comma a3, and b vector is b1 comma b2 comma b3, that is a1i plus a2j plus a3k. This is the short form. Similarly, b1i plus b2j plus b3k, this is the short form. So the cross product of this a and b is denoted by a cross b. So this is the determinant. So how can we find the determinant? First, we have to write the unit vectors that are the standard basis vectors I, j, and k. Then the components of a, that is a1, a2, a3. Then the components of b, b1, b2, b3. So we know how to find the value of determinant. So here we can see that there are 3 rows and 3 columns in this determinant. So first we have to work for I. So whenever we are working for I, then this corresponding column and this corresponding row will not be considered. So I, actually we are going to find the minors of this I. Minor is a term from determinant. So we can think like this way: whenever we are having the minor of I, then we can cancel out this column and this row. So we have this. So from here we can use cross multiplication, that is a2 b3. then there will be a minus a3 b2. Then we have to place minus. So after this we have to work for j. So minus j. Whenever we are working for j, then this corresponding column and this corresponding row will be cancelled out. So we have a1, a3, b1, b3. Now we can do the cross multiplications. That is a1, b3, negative. Always there will be negative a3, b1. So after this we have to work for k. So this time it will be plus. So plus k. So whenever we are working for k, then this corresponding column and this corresponding row will not be considered. So we have a1, a2, b1, b2. Again, we are using the concept of cross multiplication. So we have a1, b2 minus a2, b1. So this is what we know as cross product of a and b. So this is the formula. We have to have the concept of determinant, then it will be easy to calculate. Let's say we have two three-dimensional vectors. Say a equals I plus 3j plus 4k and b equals 2i plus 7j minus 5k. So if we need to find the curl of these two vectors, we can see that all these two vectors are three-dimensional. So we can find the components, that is 1 comma 3 comma 4, and here we have 2 comma 7 comma minus 5. So the cross product of a and b will be the determinant. So first I, then j, then k. Then the components of a1, a2, a3. So it is 1, 3, and 4. Then the components of b vector 2, 7, and minus 5. So first let's work with I. So whenever we are working for I, then this column and this row will be cancelled. So we have this one, that is 3 times minus 5, that is minus 15, negative 4 times 7, 28. Then there will be a minus. Now we have to work for j. So j vector. Now this corresponding column and row will not be considered. We have the multiplication of 1 and minus 5, that is minus 5, negative 4 and 2, 8, plus k vector. So whenever we are working for k, then this row and this column will not be considered. We have the cross multiplication of 1 and 7, that is 7, negative 3 times 2, 6. So we are getting minus 43i. It will be minus 13, minus minus plus 13j plus 7 minus 6, 1. So 1k. So this is the cross product of a and b, that is minus 43i plus 13j plus k. So we can understand that by cross product of two vectors, we are going to have finally a vector minus 43i plus 13j plus k. Since we have I, j and k, so that means the result is a vector. So cross product will always give us a vector. But in the case of dot product, we have two vectors whenever we are finding the dot product. So by dot product, we are going to have a scalar quantity. That means we will get just a number. So this is the difference between dot product and cross product. Dot product will give us a scalar, and cross product will give us a vector. So these are the basic concepts what we need for vector calculus. Now we are ready to start vector calculus.